Hello and welcome to section 8.1. We're going to be talking about greatest common factor and prime factorization for this section. The ultimate goal of this section is to get you comfortable with being able to write the prime factorization of numbers, and then also finding greatest common factor not only with just numbers but also monomials. So essentially those situations where you have a term of like 3x squared or something like that, finding the greatest common factor of 3x squared and maybe 17x. All right, so you're going to be doing that today. So let's start off with the first little thing. What is prime factorization? Well, prime factorization is breaking down a number into its prime factors. Breaking down a number into prime factors. So if you were then to multiply all those prime factors together, you will get that number again. So let's start off with the number 60 here. So the number 60, it can be broken down into 2 and 30. Could also be broken down into 6 and 10. That's perfectly fine if you were thinking that way. Doesn't matter, just as long as you eventually end up with the same answer as this one. So 30 can then be broken down into 2 and 15. And then 15 is broken down into 3 and 5. And right here, these are the prime numbers. If they were multiplied all together, they would get us 60. So 2 times 2 times 3 times 5. So this can be a final answer, or we can also rewrite this as 2 squared times 3 times 5. A different form of that final answer. Now I'm also going to show you one other way that we can do prime factorization. So this is what I call the upside down birthday cake, or the stair method. So if you were to divide that by 2, 60 can be divided by 2 because it's an even number, and we know 2 is the only even prime number, so we can divide it by 2, and we end up getting 30. 30 can then be divided by the prime number of 2 because, again, it is an even number, and we end up with 15. And last but not least, we have 3 and 5. Those can also do it. And here is our same prime factorization, exact same answer, just a different way of looking at it. So that's kind of cool, 2 different ways of doing the prime factorization. So prime factors are really helpful when we go to find our greatest common factor. Greatest common factor means exactly what it is. It is the greatest common factor. Well, really, what does that mean? Let's put this into layman's terms. It is the factor. So I use the exact word that's there. It is the factor. So if you're looking at the number 12, we have the factors 1, 2, 3, 4, 6, and 12. So those are all factors of 12. It is the factor that, I'm going to erase that. That is poor writing and penmanship on my part. It is the factor that is shared between 2 numbers and is the highest of the shared factors. Okay, so let's actually find the greatest common factor of 24 and 60. So we can do that by doing the factors of 24. We got 1, 2, 3, 4, 6, 8, 12, and 24. And then of 60, let's figure those out. 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. So you can always check and make sure if you've gotten all the factors by doing the rainbow method. You could always say, okay, 1 and 24, yep, they group up. 2 and 12, 3 and 8, and then 4 and 6. And then you can do that same thing with the 60. But either way, we're looking for the greatest common factor. If you look at here, we can start at 1. 1 and 1, yep, those are in common. 2 and 2, oh, it looks like we got more. 3 and 3, 4 and 4. And there's no 5 that they share, but 6 and 6. After that, it gets too big. So 6 and 6. 6 is our greatest common factor between 24 and 60. So that is one method you can do. Now if you look at 60, there are a lot of factors here, and it's easy to miss a few. We missed a few in class almost. So just looking at that, we know we can easily make mistakes. Well, another way to not make mistakes, especially when you're dealing with really big numbers, is to look at the prime factorization of those numbers and figuring it out that way. So let's do that with 18 and 27. So we need to find the greatest common factor of 18 and 27, and the way we're going to do that is by looking at the prime factorization of these numbers. So 18 can be broken down into 2 times 9, which is also equal to 2 times 3 times 3. So the prime factorization of 18 is 2 times 3 times 3. All right, so then 27, let's look at 27, the prime factorization of 27. 27 is essentially 3 times 9, and 9 can be broken down into 3 times 3. So we have 3, I'm going to do this, and I'm going to line things up a little bit. 3 times 3 times 3. Now the reason why I'm lining things up is because there is no 2 that takes care of 27. But there are 2 3s. We have 2 3s right here. We have 3 times 3 here, 3 times 3 here. They are in common with each other in the 18 and the 27. So essentially we can take these 3s down. We have 3 and 3 here. And we get 3 times 3 equals 9. So final answer for this baby is GCF of 18 and 27 is equal to 9. There's our final answer. Now we can also do that by listing out all those factors. So we could also say 1, 2, 3, 6, 9, and 18. And we can do that also for 27. We'd get 1, 3, 9, and 27. And so in this case, yes, we were spot on right, and maybe prime factorization was a little more difficult, but you can see with numbers like 60, where there's tons of factors, that this prime factorization method could be incredibly useful and helpful for figuring all that out. Okay, so we know how to use the prime factorization method to essentially find the greatest common factor. Now we're going to up the ante a little bit. We're going to find the greatest common factor of monomials. So that is the whole goal of this chapter, finding the greatest common factor of monomials. So monomials, in all reality, let's think of them as the same thing as a number. So let's say 3x to the third. That's the same as saying like 27. 27 is 3 times 3 times 3. Well, let's break down 3x to the third into its basic parts. We have 3 times x times x times x. Okay, so we've just broken that down. And then let's look at 6x squared. If we look at that, we have 2 times 3 times x times x. Same thing. We got 3's in common, and we have an x in common and another x in common. So if we were to drag that all down, we have a 3, we have an x, and we have another x. So our greatest common factor is 3x squared. So the GCF of 3x to the third and 6x squared is 3x squared. Done. Cool. Last one. And then you'll be able to do the homework. So the last one, we have 4x squared and we have 5x y to the third. So let's break this down. 4x squared, we can rewrite that. Let's start first with the number 4, can be broken down into 2 times 2, and then x times x. And you notice I just made a space right there, and I want to show you why just down in this next part. We have the number 5 here. 5 can't be broken down into 2s. 5 is just simply 5. Look how I've aligned that. I've aligned that so that way they're all kind of next to each other. And now I have an x, so we have times x, and then we have 3 y's. So we have times y times y times y. Now let's align things. What do we have in common? I just simply see a single x in common. The 2's don't work. The 5 doesn't work. They're not in the top or the bottom. in both places. We don't have 2 x's in the top and the bottom, and we don't have 3 y's in the top and the bottom. They're just in the bottom. So the only thing that can be brought down for this one is simply x. So our final answer for this, we can say the GCF of 4x squared 5xy to the third equals x. Final answer. Now what we can also say is if this x weren't in our original equation for the 5x, and we had 4x squared and 5y to the third, we can see already that since the x is gone from the 5, the greatest common factor for this situation is going to be simply 1, because there is nothing else that they have in common. So go ahead, begin the homework, start it, have fun with it, and I will see you guys tomorrow.